Hello students, today we are going to discuss on a topic of how to find electric field due to an electric dipole. So the first case is how to find electric dipole on the axial line of the electric dipole. The second case is how to find electric field on the equatorial line of the electric dipole. So let me discuss the first case, that is how to find electric field on the axial line of electric dipole. So now let me draw a dipole first. What is a dipole? A dipole consists of two equal and opposite charges. Here two charges, this is minus q and the plus q charge. So this is dipole and it must be separated by a certain distance, that is 2a. Let the length of the dipole be 2a. So this is a system of two equal and opposite charges separated by a certain distance, that is 2a. So it is an electric dipole. Let O be the center of the electric dipole. Now our target is to find electric field on the axial line of the electric dipole. So this is an axial line. So let us consider any point P on the axial line of the electric dipole. So this point P is at a distance r from the center of the dipole. So now there must be two electric field at point P, with whom due to minus q charge at A and the due to plus q charge at B. So let me consider the electric field due to minus q charge at A at point P will be EA here. Now you will ask question, why EA and along this direction? What is the purpose of putting an arrow in this direction in the electric field? Because this is a negative charge and the electric field is always towards the negative charge. And now electric field due to plus q charge at B is given by EB here. EB here. So why you are asking a question that why the electric field is moving along this direction? It is because it is moving away from the positive charge. So electric field. Now we will write, consider an electric dipole of length 2a. Electric dipole of length 2a. Let P be any point on the axial line of electric dipole. Let P be any point on the axial line of the electric dipole which is at a distance r from the center of the dipole. Okay, this point P is at a distance r from the center of the dipole. Okay, now let us write the electric field at P due to minus q charge at A. Electric field due to minus q charge at A. Electric field due to minus q charge at A is at point P. Electric field at P. Electric field at P due to minus q charge at A is, I will write it as EA. I will write the magnitude K Q by A P square, and I can write this as K Q by A P square is what? R plus A whole square. So this is the required magnitude of electric field at point P due to minus q charge at A. Now I will write electric field at P due to plus q charge at B. Now I will write what is electric field at point P. At point P due to this charge at B. So it is EB. I will write the magnitude of electric field at K equals to Q by B P square, and it is K Q by R minus A whole square. That is the distance square. So distance from here to here is R minus, this is A and this is A. So R minus A would be equal to BP square. Okay. Now R minus square A square is BP square. So now we got EA and EB. Now since EB magnitude greater than EA and E, EA and EB are coaxial. Now look at this, EB is greater than EA. Why? Because R minus A and R plus A. Here R minus A is smaller than R plus A. So obviously EB magnitude will be greater than EA magnitude. So EB greater than EA and EA and EB are coaxial. Therefore, the electric field on the axial line is equal to EB minus EA. The magnitude of electric field on the axial line will be EB magnitude minus EA magnitude. So let us write what is EB magnitude. E axial magnitude is equal to EB is K Q by R plus R minus A whole square minus K Q by R plus A whole square. So now I will write a common of this, K cube common, 1 plus R minus A whole square minus 1 by R plus A whole square. Now this further can be written as K cube. Here, if I take the LCM of this, then R minus A whole square and whole square here. R square minus A square whole square, and the numerator will become 4AR. The numerator becomes 4AR after the simplification. Okay, after simplification we get 4AR. So this further can be written as KQ. 4AR I will write as 2 into 2AR divided by R square minus A square whole square. So this further can be written as K Q into 2A. I will write 2A here and the Q here. So I will write 2 into P dipole moment, the magnitude of dipole moment, and the R divided by R square minus A square whole square. So this is the magnitude of electric field on the axial line of the electric dipole. And now you will find that magnitude on the axial line is 2 times K ER, and the direction of electric field will be along the direction of the dipole moment. The direction along P. The direction of electric field resultant electric field will be along the direction of the dipole moment. So there is a required expression of electric field on the axial line of the electric dipole. Now, then what we can consider here is one special principle is one case can be considered, case number 1, if A is very smaller than R. This case is okay applicable for an ideal dipole. For an ideal dipole. For an ideal dipole, we can consider that A is very smaller than R. So we can write this equation. Then E axial can be written as here K here, 2 here, P here. Okay. And now this R square into square, R power 4, because A is neglected. So we get R power 4 and R cancel, R cube. Okay, so in this case what we get, then we all find that the final result for E axial is inversely proportional to R cube. Okay, inversely proportional to R cube. Now, if we plot the graph, then it will be the graph of the nature of the graph will be somewhat like this. Yeah, this is R and this is E, and the nature of the graph will be somewhat like this. Okay, so this is a required expression for electric field on the axial line of electric dipole. One more interesting thing here is whether the electric field will be 0 at any point on the axial line of the dipole. And the answer will be no. Why? Because at any point here, the electric field E and E will be completely different from each other. If you can take a consider a point here, then also electric field EA and E will be different. So there is a difference, it can never be zero. Another case, if you take in the middle and between them, then electric field will be in the same direction. So it is minus Q charge, electric field EA, and this is EB also in the same direction. So here electric field can never be zero because they are not subtracted, they are added at the same time. So electric field on the axial line of electric dipole can never be zero. Okay, so we are going to repeat in the next. Okay, for the next discussion, next case on the equatorial line in my next discussion. Thank you.